Hello everyone, I am Seshavitya, working as Associate Professor in the Department of ECE at R.M.K College of Engineering and Technology. So welcome to this session. So in this session we are going to discuss what is loading of transmission line and what are the types of loading. So before going into this, what is loading, and we should consider and what is distortionless line. So in your last session we have just discussed what is distortionless line is. Okay, so there are two types of distortions that may occur on the transmission line. One is frequency distortion, second one is phase distortion. Okay, so there will be just deriving one condition that if there should not be any, that is neither frequency distortion nor phase distortion, the condition is that Lg should be is equal to Rc. Lg, that is inductance and conductance, and that should be is equal to R into C. So Lg should be is equal to Rc. And this condition, if any transmission line which satisfies that condition, then we can call it as distortion. But practically speaking, so this Lg is equal to Rc is not possible in practical case. So which means for the practical transmission line, this R by G ratio will be greater than that of L by C. So what you have to do? So to make this ratio both equal, so there is a necessity of loading, which means we will be just considering all other conditions, and if is there any possibility of increasing resistance, or if there is any possibilities of decreasing the conductance, or by increasing the value of C and by increasing the value of L. So finally we will be deciding that only by increasing the inductance value we can able to achieve this condition Lg is equal to Rc. So that increase in that is loading of that inductance on the transmission line is nothing but loading. So which means increase in that inductance on the transmission line is nothing but loading. So there are two types of loading. One is continuous loading, other one is lumped loading. So what's the basic difference between these two is, in case of continuous loading, so we'll be adding that inductance by means of magnetic tapes. That is the magnetic tapes that can be wounded on the each conductor. So likewise we can able to increase the inductances. So that is nothing but continuous loading. And in this case of continuous loading, we'll be just loading that magnetic tapes throughout the conductor. Lumped loading. So lumped loading is nothing but, so you'll be just loading that inductance. That is, we are just adding that inductance by means of at equal distances. And we can just call it as a section. So that inductance sections that can be added at equal distances. And for example, you can say that it may be in terms of lumps at uniform distances. That is why it is called as lumped loading. Okay, and one more thing is, in case of this lumped loading, in this inductors are introduced in both the limbs to keep the line balanced one. Okay, so this lumped inductors are in the form of coils, so that we can call it as loading coils. So okay, so this is about the lumped loading. So before going to this lumped loading, first we'll consider what is continuous loading is. So for continuous loading, so this is the increase in the inductance for continuously loaded line. So this is the equation, and then we'll be just considering the propagation constant for continuously loaded cable. So there we'll be assuming that conductance G is equal to 0, and at the same time L is increased in such a way that omega L should be greater than that of R. So then we can write that what is series of impedance and shunt term admittance according to this condition. And finally we can able to derive the equation for alpha, beta and velocity of propagation. And here there is a condition that, and if you want to make this condition, that is Lg is equal to Rc, there are two conditions arises. One is alpha and the velocity of propagation should be independent of frequency. That is first condition. Suppose if you want to keep that velocity of propagation independent of frequency, then beta value should be in a direct function of omega, that is frequency. So by considering that condition, we'll be deriving that equation. So if you just look into this equation, we can able to see what is it alpha. Alpha is totally independent of frequency. There is no frequency term at all. And similarly, velocity of propagation, it is also independent of frequency. There is no omega term in this equation. And the second condition is that the beta value should be direct function of frequency, since omega is nothing but 2 pi f, so it's a direct function of frequency. So only this way we can able to achieve that distortionless line condition. So accordingly, we are just deriving these equations. So next, coming to that characteristics impedance Z0, we know that it is root of Z by Y. So you can just substitute R plus J omega L by G plus J omega C. So according to this continuously loaded cable, we will be considering omega L is greater than that of R, and at the same time G is equal to 0. So substituting, that is, we are just neglecting that resistance, and G is equal to 0, so that we can write it as J omega L by J omega C. So J omega get cancelled. So finally we can write that characteristics impedance Z0 is root of L by C. So from this equation we can say that this characteristics impedance is also independent of frequency. So likewise we can able to increase the inductance on the transmission line continuously. And under these conditions we'll be just noting all other points. What are the points we discussed? Here it is written here. And then advantages and disadvantages. By using this continuously loaded cable, and we can say that attenuation is independent of frequency as I told you, and alpha is, that is attenuation constant, that can be decreased by increasing the L. At the same time, that R value should not be increased greatly. And the third advantage is that we can able to increase that inductance up to 100 millihenry per unit length, and only up to that point is possible in case of continuous loading. Then what are the disadvantages? So this continuous loading is very expensive, and second point is that which achieves very small increase in the tel per unit length. As I told you, we can able to increase, that is we can just able to load up to 100 millihenry per unit length. That is also a disadvantage. And the third disadvantage is that so that the existing cables, existing lines that cannot be modified by this method. That is only replacement is possible. We cannot modify that existing lines. So these are the advantages and disadvantages. So to overcome these disadvantages, we go for the loading. So this is about the lumped loading. So you'll be just loading that inductance by means of lumps at equal distances on both the conductors. To make that both the lines balanced one, so you'll be just adding that inductance in terms of lumps at equal distances. And this is the characteristics curve which shows the attenuation versus frequency characteristics curve. And from this we can able to see that for continuously loading cable, and here it is continuously loading is totally independent of frequency. But in the case of lumped loading, after that cutoff frequency, there is a sudden increase in the alpha value, that is attenuation value. So this is the difference between continuous and lumped loading with respect to the alpha. And here to solve this, that is to find out that alpha, beta and z0 value, we'll be just considering that Campbell's equation. So in this we'll be considering one symmetrical T section, and from the center of one loading coil to the center of the other one. So likewise we'll be just considering that symmetrical T section, and this equivalent T section for a part of line between two lumped loading coils of impedance ZC. Okay, so likewise we'll be considering. So this is ZC is nothing but, here it is center of the coil, that is a lumped coil, and this is also the left hand side is nothing but it is also center of the lumped coil, so that it is ZC by 2, ZC by 2. So by considering this, so we'll be considering that N. So here this N represents number of miles between the loading coils, and gamma is nothing but, as we know, it's in propagation constant per mile. And before loading of the line, for the length N and for the T section values in terms of Z0, we can able to write here. So here it is sin h N gamma, which is equal to Z0 by Z2. Similar way, cos h n gamma, which is equal to 1 plus Z1 by 2 Z2. So from this loaded line and that equivalent circuit, we can able to write this. And when this loading section is added with the actual symmetrical T section, then we can write that series sum impedance as Z1 dash by 2, which is equal to ZZ by 2, which is nothing but center of the lumped loading, plus as usual the series sum impedance Z1 by 2. Since it is in symmetrical T network, so it is Z1 by 2. And there is no difference in that shunt arm impedance, that remains same, which is nothing but Z2. So from this first equation, we can able to write what is Z2 is equal to. From this we'll be solving what is Z1 by 2 just by rearranging this equation. We'll be writing that what is Z1 by 2. So we got that Z1 by 2, so that can be substituted in the equation. So by substituting and just rearranging this equation, finally we can able to write what is cos h n gamma dash, and that is equal to cos h n gamma plus ZC sin H n gamma by 2Z0. So this final equation, which is also called as Campbell's equation. So what's the purpose of this Campbell equation is that which permits the determination of the gamma end of a line which consists of partially of lumped elements and partially of distributed elements. So it has two factors. One represents partial elements, that is lumped elements. The other one which represents the distributed elements. And this Campbell's equations which will make the which makes it possible of calculation of the loading of coils in reducing the attenuation and the distortion on the lines. So it will reduce both attenuation as well as distortion on the transmission line. So that is the main purpose of this Campbell's equation. So now we can just look into that what are the advantages and disadvantages. And as in the case of continuous loading, we know that we can able to increase up to 100 millihenry per unit length. But in this case, there is no limit on increasing that inductance. So we can just increase even above the 100 millihenry. And in that first case, continuous loading, that was very expensive. But here it is cost is very small. And in that previous case, the main disadvantage is that existing lines cannot be modified in the case of continuous loading. But here we can able to modify. So these are the advantages of lumped loading when compared to the continuous loading. So all the disadvantages of continuous loading are overcome by using this lumped loading sections. And then what are the disadvantages? It has two main disadvantages. And for a cable, we'll be just using the shunt arm impedance Z2. And that Z2 as shunt arm impedance is capacitive. And already the cable capacitance plus lumped inductance which will form the low pass filter. So if it is in low pass filter, obviously as I told from this graph, after the cutoff frequency, there will be a sudden increase in the attenuation value. Okay. And this attenuation that can be reduced below that cutoff, but above the cutoff there is a rise in the attenuation. Obviously if attenuation increases, what will happen? Which will in turn decreases the efficiency. Okay. So this is about the lumped loading. So I think familiar with this what is continuous and lumped loading. And next one is reflection on a line not terminated in Z0. That is when the receiving end impedance is not terminated by its characteristics impedance, then what will happen is obviously there will be a reflection. So reflection occurs. So if the line is not terminated in Z0, then we can write it what is voltage and current equation. And if any voltage or current equation which will consist of two factors, that is two components. One is incident wave, the other one is reflected wave. The component with e power gamma s is nothing but incident wave. The component with e power minus gamma s represent reflected wave. So for simplicity, I'm just considering the voltage equation here, so that we can just write that incident voltage as in this equation, and by making Z0 is equal to ZR, so that the second term becomes 0, so that we can write it as E1 is equal to ER of ZR plus Z0 by 2 ZR into e power gamma s. As I told you, the component with e power gamma s which will act as an incident voltage. Since it's an voltage, so we can call it as incident voltage. So similarly, we can just write it for reflected voltage. So ER of ZR minus Z0 by 2 ZR e power minus gamma s. So the component with e power minus gamma s which will act as in reflected voltage. Okay. And if ZR that is tends to infinity, then that is nothing but open circuit condition. We can write the incident voltage and reflected voltage. And this graph which represents the voltage waves for open circuited line at time instant t is equal to 0 and at time instant t is equal to 1 by 8 f. Okay. So what's the conclusion is that if the line is not terminated by its characteristics impedance, then there exists reflection. So which means if you know, in order to make that reflection as minimum or 0, it is necessary to terminate that ZR, that is receiving end impedance, by its characteristics impedance. So therefore only when ZR is equal to Z0, so we can just say that there is no reflection at all. The same line which is also called as smooth line. The line without reflection is called as smooth line. Okay. So since if ZR is not equal to Z0, as I told you, there exists reflection. So what are the disadvantages of reflections? So reflection is undesirable on transmission line. So this reflected wave appears as echo on the sending end. So whatever the signal which is sending from the transmitter, which will be reflected back. Suppose if there isn't reflection, then there isn't reduction in the efficiency, as I told you. Okay. And one more thing is, and if the impedance of the generator is not equal to Z0, then reflected wave is reflected again and again, and which will reach this sending end, and which becomes a new incident wave. So what will happen? So the transmitted back, that reflected wave, which is transmitted back forth and that is back and forth. So there will be a dissipation in the line. So this is about the reflection on a line when the transmission line is not terminated by its characteristics impedance. In order to make that reflection as zero, then we have to consider that factor called reflection coefficient. So what is reflection coefficient is? It is the ratio of reflected voltage at the load to the incident voltage at the load. Or other words, we can say that the reflection coefficient which measures the that is mismatches between ZR and Z0. So as I told you, we'll be considering that voltage equation and we'll be writing that what is incident wave equation and reflected wave equation. Substituting in this equation, we'll be getting ZR minus Z0 by ZR plus Z0. This is nothing but reflection coefficient. So only based upon this reflection coefficient, we can able to say whether there is a reflection is there or not. So for example, we'll be considering three cases. And here when ZR is equal to Z0, that is if the receiving end impedance is it's perfectly terminated by its characteristics impedance. Substitute this condition in this case, what will happen? So this K becomes 0. So which means if reflection coefficient is 0, so obviously we can say that there is no reflection at all. Similar way, by substituting second condition, if the receiving end impedance is equal to 0, that which means what? When the line is short circuited, then we can substitute that condition here. We'll be getting it as minus 1. Minus 1 you can add it as 1 with the angle 180, which means K value is equal to 1. So what will happen? So if K is equal to 1, which means their reflection is maximum. Similar way, third case we can just consider when the ZR is equal to infinity, when the line is open circuited. If you substitute this condition, then K becomes 1 with the angle 0. So again reflection will be maximum. So what's the conclusion from this reflection coefficient is that the reflection coefficient K, which ranges from 0 to 1. Only when that K is equal to 0, there is no reflection at all. Other than that K value, that is other than that 0 value, there will be a reflection. At the maximum when K is equal to 1, there will be a maximum reflection. So in order to that is remove the reflection, or in order to eliminate the reflection, the condition is that K value should be is equal to 0. If you want to make that K value as 0, then we have to make that ZR is equal to Z0. That is the receiving end impedance that has to be terminated by its characteristics impedance. Okay. So I hope you understood this all the topics in today's session. Thank you.